Okay, there's going to be basic counting. These are going to be used in probability. If you have done any probability course, you should be familiar with these. In some statistic courses, they go with the probability bet, and that's why in your book you see one chapter on probability. But we don't, we are not going to cover it. It's not a part of the content of the discrete mathematics course in this college and at the university. Okay, so this Bayes one is basically the one that we use in the statistics, but in your case, you're going to use it in a couple of places. This is going to be called addition rule. Okay, so it's going to be addition rule. We're going to have something like 3 problems on this one, 3 nice one. Okay, so what's going to be the addition rule? We are going to consider, you say this is going to be, suppose 2 sets are given to you. So suppose and the sets A and B are given. Okay, so this is going to be the set A with some members in it. Okay, and we have another set, and this is going to be the set B. So it's going to be A and the B. Okay, so we have some members in A. So these are going to be the members in A. Okay, and we have some members in, okay, some members in B. So this is going to be the one. Okay, so we are going to use this notation. N of A means the number of the elements in A. Okay, it's going to be number of elements. Okay, number of elements in A. That's going to be N of A. Then we are going to have N of B. Okay, N of B is going to be number of elements in, okay, elements in B. These are going to be the one. So what we are going to be interested in, we want to know what is going to be the number of the elements. Okay, we want to know what's going to be number of the elements in A union B. You see, that's going to be the one that we're going to be interested in. A union B, you know that. The members in A or B or in both of them, do we know to get this number. So if we want to do it naturally, we are going to count how many numbers are going to be in these, okay, those sets. So if you take the N of A, you see N of A would be what? Would be 6 members. So that gives you 6, that's going to be N of A. Then if you check N of B, okay, N of B, what's that? It's going to be 6 and 2 would be 8 elements. That's going to be 8. Okay, and now if you want to count how many members are going to be in A union B, okay, A union B, any suggestion?
12.
It's going to be 12. Yes, very good. 12. It's going to be 12. Okay, that's going to be 12. And how many members do we have in A intersect A intersect B?
2.
It's going to be 2. Very good. You see, the question is going to be, we want to know what's going to be a relationship between these that we put over here. Okay, the relationship that you are going to have here, you see, if you want to count the members in A union B, naturally, you are going to count all the members in A. You're counting all the members in A, then all the members in B, all the members in A and the B. If you count only the members in A, this is going to be 6 elements. And if you count the numbers in B, that would be 8 elements. So if you put them together, that gives you 14. But if you do 14, there are going to be some numbers that you counted twice. You see this black one? It's going to be counted once as a members of A and once as a members of B. So in the counting, you must make sure that you are going to count each member once. So that's why we have to exclude this second counting, if you like. You see, that's going to be the one. So the argument is going to be the conclusion, if you like, is that if you want to find the members, okay, if you want to find the total members in A union B, yes, you are going to count the members in A, then you add it in the members in B. Okay, but you have to exclude that repetition. That repetition is going to be the one that's going to be in your the intersection. So the intersection one, you are going to count it only once. So since you want it twice here, once with the A, once with the B, then you have to subtract that extra times that you buy. You see, that give you the formula. Okay, so in order to find the members in A union B, you are going to include the members in A and the B, but you have to exclude the members in the intersection because otherwise you are going to be counted twice. Any question? This easy observation we refer to it as a inclusive or inclusion. Okay, we call it okay, this is it. It's going to be inclusive, exclusive, or exclusion. Okay, exclusive formula or just a principle, criterion, something like that. You see, that's very nice observation that would have a very important applications that we're going to have. If you are going to be in a probability course, you divide this one by the total number in the, we call it a sample space, like something like universal set. And then this is going to be probability of A or B, which is going to be probability of A plus probability of B minus probability of A and B. That's the way we are going to use it in a probability course. But in this course, we are not going to be interested. We are going to be interested in counting procedure and the problem related to that one. Any question? Now, this is just for 2 sets. We can extend it to the 3 sets, okay, because we need it. We need for the 3 sets, 4 sets in general, n sets. Okay, so more generally is the fact that if you give me 3 sets, okay, if A, B, and C, okay, are going to be given sets, and these are going to be given sets, and then let's see what would happen then. You see, in this case, the situation is going to be, this is A, this is going to be the set A, okay, and this is going to be the set B, this is going to be a set B, and you're going to have another set, okay, and this is going to be the set C. So again, the same procedure. You must make sure that you're going to count the members in each set only once. So what's going to be the result? The total numbers in A union B union C is going to be the members in each set. So it's going to be n of A, okay, plus n of B, plus n of C. You see, then you have to exclude those intersections. Now you have to exclude the 2 by 2 intersections. Then you have to exclude minus n of A intersect B, okay, minus n of A intersect C, minus n of B intersect C. You see, but the difficulty is going to be when you take out all these intersections, and there is going to be a part that is not going to be never going to be counted. You see, when you exclude all these 3 intersections, there is this part. You see this part over here. You see, this is the one that is contains in A, B, and C. So if you take out all of these, automatically this would taking out. So this portion never be counted. So that's why you have to include that. It's going to be a plus. plus n of A intersect B intersect C. So that would be your formula. So again, it's going to be, you are going to be including the members in each set, but you're excluding the 2 by 2 intersections, but you have to include the intersection of all of them to get the final answer. And it's going to be the same for, you can go with the 4 sets. We can go with the n sets. You have some cases in your field, then you have to do that one. It's kind of A1, A2, A3, A4. Then you just check these intersections together. Okay. So that would be for the 3 sets, and in general for, you can go for the n sets. So first, I rewrite it. This is the way we are going to rewrite it, because we have the 3 by 3 quite a lot in those problems that we have. So A union B union C, it's going to be just include these. Okay. So you include each members. So exclude the 2 by 2 one if you like. You can use this notation. Okay, so it's going to be A intersect B, A intersect C, and B intersect C. Then you have to include n of A intersect B intersect C. This is another version that you may think about it to get this formula. And the problem that we're going to have is going to be regarding these 2 terms. You see, sometimes all the information to the right would be given, then this would be the unknown. But sometimes the unknown would be given to this part would be given, and then the question is going to be, you want to know how many members are going to be taking something. These are everything in common, if you like, depends how we're going to define it. When we say the union means, if you get an X, when we say X is in the union of these 3 sets, this means at least X belongs to one of them. You know that the definition. X is in A or B or C means at least X belongs to one of them. But when you take A intersect B intersect C, this means A belongs to each of them, okay, or all of them. X belongs to A, belongs to B, belongs to C. So this is 2 different interpretations that we're going to have. Okay, any question? So that's called addition rule. So what we're going to do, we are going to give you some problems. Okay, actually it's going to be 3 problems. You have to design it. You have to design it. You have to tell us what is ABC. Okay, you have to connect, and then you write the formula, and the substitute give us the result. Okay, so without formulas, we don't accept it. It doesn't make sense. You have to tell us how do you design it, because some of these problems can be solved, differently. But we want to use these famous notions. Okay, so there are a kind of 3 problems, 3 types. The first one is very classic. All the information nicely would be given. This would be your understanding, reading the context and understand, pick up these quantities. You're not going to do anything extra for us. The second one is one famous problem in arithmetic, divisibility. You want to know how many numbers can you find that are going to be, okay, how many numbers less than 1,000 are that are be divisible by something like 2, 3, and 5, or 2, 3, or 5. So these are going to be divisibility, a nice one. And the other one is a very interesting one, is you have to wait to get something else. Then we have some equations. We are going to call them integer equations. You see, when you solve equation like x plus y equal to the 5, then x and the y are all real numbers. But in counting problems or in discrete mathematics, we use integers, that, dot, dot, dot. So it would be a source of many, many interesting, interesting ideas. So let's give you one to get to know it. Okay, any question? So this is your tool. We call it addition rule. Very popular. This problem was around for a long time, but basically for the problem of, okay, it's for probability problem. But because of the computer science, it just came back again, if you like, regarding these counting problems. And it starts with a very interesting problem. That problem is going to be called, they call it hat problems. Let's see, let me just, I may have it because I gave a talk on this one. If I can show you this one, it's an interesting one. After these type of problems, there was a case that, everybody got interested in these type of problems. I used to have a copy of the original paper. If I can find it now, I tell you, otherwise I look for it at the end of the lecture. The probably there was somewhere that I had it. Let's go no, I cannot find it quickly, but I usually keep these articles. But anyway, I will, at the end of the lecture, I just go for it. No, I'm sorry. I should have it. I bring it back and tell you what's this about. And the idea is, I can give you the story. The idea is, it's an English problem. So the people going to a restaurant, for example, when you go to a restaurant or to a hotel somewhere, you have your coats or your umbrella, your hat. You just go to the desk. Receptionist will take your umbrella, your overcoat, and then will give you a number. Okay, you keep the number. When you come back, you expect to get your coat. Okay, you produce the number, the receipt, and they just give it to you. But the guy who was hired to do this, he was new. So as soon as he got the hats, he just gave you your number, but he just put the hat whatever, wherever he likes. So when you come back, there is a possibility that you are not going to get your hat. So there is a very famous problem that, it's something like 64 something people, a group of the people. We want to know how many ways exist that you are not going to get your own hat. Okay, all the people that we're going to have. Okay, so in order to solve that problem, you need this idea that you are going to create different sets, the sets that the possibility that you are going to get your hat and get this result. I come back to it. I need something else. Then I come back to you and show you that very famous problem. And then it becomes very popular in some part of the idea of the computer science. Okay, so just to give you a motive of these type of problems, but the one that we have, you have 3 problems in your book, very similar to this one. And I will post the practice quiz. You will see 2 of those problems. This is just a straightforward one. We check your understanding of the problem. It would be a long story in this one and the one that you have, but you have to read it carefully and you connect. So this is the question. We have a group of students, they have different courses and we check those. Suppose that 100 of 120, okay, mathematics students, a student, okay, at Palmer College, at a college. Okay, at the college, take at least, take at least one of the following. One of the, okay, one of the following languages courses, like languages, The languages are going to be, we have a French. Okay, we summarize it at F, okay, as French. The other course is German. Okay, so that's going to be the next course, German. These are different categories that we're going to identify, and the Russian. So the French, German, and okay, Russian. So this is going to be R. So we have the math students who are taking these languages courses, okay? So also we have this information. Also, we know that suppose 65 students, 65 of those students study French. It's going to be French. Then 45 students study German. Okay, that's going to be study German. We have 42 study Russian. Okay, 20 study French. Study 20 study French and German. French and German. Then 25 study French and Russian. French and Russian. And 15, okay, 15 study German and Russian. The one in your book is just computer science, like Java, different courses that you have, CS 101, etc. So we may make up something similar for you. Okay, so what's going to be the question? The question is going to be, we want to find the number of, okay? Find the number of, find the number of students, who study all three languages. All three languages. Okay, so that's going to be the question that we have. Okay, so you have to make up those categories that we're going to have. You see, the categories that we talk about it are going to be the French, German, and Russian. So this simply means you want to find the number of the people who study all the languages. So this means studying the French and German and the Russian. So this means the question is going to be, what's going to be the number of the N of F intersect with G and intersect with R. You see, that's going to be the way we are going to organize our problem. So we are going to introduce this category that we're going to have, and then you have to put these information into the symbolic form and then use your formula to get it. Okay, so the solution is going to be, you are going to note that this is it. Put this information into the symbolic form. The number of the people studied French is going to be N of F. Okay, so that would be 65. The number of the people studied German is going to be N of G, which is going to be 45. For the Russian, so you have 42. Okay, and this is it. Study French and German. So it's going to be French and German. French and German would be 20. The next one is French and Russian. French and Russian is going to be 25. Okay, 25, and eventually the German and Russian. German and Russian would be 50. Would be 15. So what is missing? The missing one is, what is going to be this one? Since their intersection is the question, so you need to know what is going to be, okay, this one. What's going to be the union? Okay, what's going to be the union here? So the union means you want to find the number of the students who takes at least one of these courses. Okay, so this means basically what? This means basically all the members of the class. So look at this one. Suppose 100 out of 120 math students taking at least one of these courses. At least one of these courses means they are going to be in the class. So this would be 100. Any question? So at least means the union. At least means union. All means, everybody. So in this case, most of the time, this is going to be the question that we're going to answer. Be the or, but I'll just give you this one because you have one in your book. So don't be surprised. You may have to do either one. Okay. So it's clear that you have to use the addition rule. So the categories are going to be the French, German, and the Russian. Write the formula, and you have all the information. That's going to be the easiest case. Just understanding and the substitution, and then you're done. Okay, any question? So write your formula. You have to give us the formula on the test, remember. Write the formula and the substitution, and then you're done. So this is it. The formula to be used for this problem is N of F union G union R is going to be equal to, include each one first, N of F, N of G, N of R. Okay, so we include each set, exclude a 2 by 2 intersection. So N of F and G plus N of F and R plus N of G and R. But remember, you have to add. You have to add N of F intersect G intersect R. That's going to be your formula. Any question? Make sure to write your formula correctly and then substitute.
Do you want us to move around the variables? So like the one we're looking for is at the end?
Yeah. We write the formula as is, okay? We write the standard formula. And then it depends whatever we have. Okay? Because most of the time this is going to be the unknown, but in this problem it's the other way around. But it doesn't matter. So we just substitute. Okay, so this is 100 is equal to this is it. You have these numbers. Yeah, just put them in the parentheses and combine them together. That would be easy. That's it. Then the 2 by 2 one. The 2 by 2 one, we have a 20, 25, and 15. Okay, and this is the unknown for this problem. Okay, this is going to be the unknown for this problem. Any question? So we substitute whatever we have. So if you add these numbers, this is it. Okay, so it's going to be 110, 152. Okay, minus, and this is going to be 40, 60. And the other one is the unknown. Intersect G, intersect R. Okay, so that would be 100. And you subtract, that give me 92. Okay, 92 plus N of F intersect G intersect R. So the conclusion is going to be N of F intersect G intersect R is going to be 100 minus 92, which is equal to the 8. So there are going to be 80 students who will take all the language courses together for this class that we have. Okay. Any question? So that's a straightforward one. You have to read it carefully, be patient, and you have a couple of them in your assignment. So if you give you this, you know how to find out. The one that we're going to be interested in, we want to do a little bit of algebra, or it's going to be the same thing, but it gets something else. But this is one option. Any question? So the one that is regarding computer science, okay, we just put them together. Somebody took calculus, okay, chemistry and computer science, then we use a similar one. So it was a little bit unusual because we usually ask for this, not the other one. But it's okay. It's okay if they ask for it. But it's not going to be the case most of the time. Okay, that's case one. Any question? Now, the next case is more interesting. The next case is something from arithmetic. Okay, this number is popular. And the way you're going to find those n of a, b, c, some people miss it on the, during the test. And there is a one different version of this that we're going to check also. Okay, so this is the one. You have something like 3 of these problems in your book, in your assignment, and get one on that practice one and the final review. That's it. We want to know how many integers. Okay, how many integers? How many integers in the set? In the set. The set is going to be n such that n is just going to be all the integers less than 100. Okay, we want to know how many numbers less than or equal to the 100 are divisible by 2, 3, or 5. That's a very popular case. Okay, how many numbers less than 100 exist that are divisible by 2, 3, or 5? That's one. That's a good we like this one because you just you design it using this type of idea. Remember, you have to use this idea. Given this one on the test, some people they list all the numbers between 1 and 100. Okay, all of them here, and then they look at it to see which one is going to be divisible by 2. Yes, that's nice, but you're not going to get any point for it. Okay, you have to use this idea of the inclusive and not arithmetic. You have to tell us how you did it. So be careful. Okay, so what we're going to do is, this is it. We are going to design it. You have to give us a design, how you connect this problem to the done when we talk about it. Don't just give us a number. Okay, this is going to be the design. We have a couple of other problems similar to this one. So we would like to design it in this form. Suppose we're going to call this just as our kind of universal sets, because there is another version of this problem that I'll talk about later. So that's why I write this type of notation. So I'm going to take this set, I call it U, because this is the set that you're going to take in your members out of it. Okay, and so what's going to be this set? This set's going to be just a 1, 2, 3, 1, 2, 3 up to the 100. So from this set, you are going to get those numbers. Okay, it's going to be the case, and you are going to suppose A to B. Okay, what is the set A? The set A is going to be all the members in U which are divisible by 2. Divisible by 2, you know that. This is going to be what? A number n in U such that n is divisible by 2 of the form of the 2k. That's a set A. Okay, nice. You design it and use just mathematical symbol to to talk about it. Divisible by 3, so get a B. Would be all the members in U. All the members in U divisible by 3 is going to be 3K. Then C. C is going to be all the members in U. That's going to be divisible by 5. Divisible by 5. Okay, so that's going to be, that's going to be for some K to get these numbers. Okay, so instead of writing down in word form, we're just using, using these symbols, divisibility by 2, 3, and 5. So now what's going to be the question? The question is going to be, you want to know how many numbers are going to be divisible by 2, 3, or 5. So this means you are interested in N of A or B or C. See? So this is how we're going to connect your problems to the inclusive exclusive principle that we are going to have. Any question? This is, you are going to write it down for us on the test, okay? Just give us the numbers, we put a question mark for you. You have to give us the theorem, design, and now we know the formula, okay? So the formula is, I'll just repeat it again. So the formula that we're going to use is going to be this one. So we have to include NA, NB, and C. Okay, all the members in each set. Then we have to exclude the intersections. A intersect B. Okay, A intersect C, and the B intersect C. Okay, and then we have to, include the intersections. N of A intersect B intersect C. Okay, you have to find these numbers, bring it up here, substitute, get the result, and be done. Now, to find these numbers for the divisibility, there is a easy method that we're going to do. Okay, so I just give you something that you can use. This is just a note that. That's for your information. Note that number of the integers less than n that are divisible by a number k, and number k is, you see, in order to find that, you are going to divide the k. Okay, you are going to divide the n by k to find it. If you want to know how many numbers less than 100 is divisible by 2, it's going to be 100 divided by 2, which is 50. But if you want to find how many numbers less than 100 is divisible by 3, 100 divided by 3. 100 is not divisible by 3. But the result must be an integer. So in order to be divided, if it's not going to be integer, we make it into integers. From algebra, we use this notation. We call it the bracket. Create this integer function, but if you don't know it, it doesn't matter. Okay, is a double bracket here. This double bracket means if it's not going to be decimals, you're going to, okay, you drop the extra part and you pick a small. For example, if you get this one, something like 33.3, you call it 33. This is going to be the smallest integer, okay. This is going to be the greatest integer, less than the actual number, using in calculus, greatest integer function. Okay, so I'm going to use this fact. I'm going to show you how I'm going to use it, and this notation. Okay, so the number, you want to know how many numbers less than n is divisible by k, n over k. If it's going to be integer, you got it. If it's not, ignore the decimal part if you like, to get it as an integer. Okay, so let me write it down so you know what I'm talking about. You see, you want to find n of a. What is a? A is divisibility by 2. So you want to know how many numbers are less than 100 but divisible by 2. It's going to be 100 over 2. 100 over 2. You can use the bracket that we talk about it, but this is already 50, so you don't need it. Okay, double bracket or just bracket for this case. You know, we accept it. Even if you use a bracket, we understand it. Okay, any question? N of B. N of B would be 100 divided by 3. Okay, so I just show you what would happen to this one. 100 divided by 3 would be 33.3. 33.3, but you'd get the integer parts. Integer parts is just going to be 33. It's going to be the largest integers less than. Okay, you cannot pick the 34 because the 34 is over. Okay, below, you see, any largest, closest integers to the 33.3 is going to be the result, 33. Any question? You cannot have 30, some people write 33.3, doesn't make sense. You cannot say that there are 33.3 numbers divisible by 3. No. Okay, so just use this if you need it. N of C, divisibility by 5. We don't need any bracket because the 100 is divisible by 5. Okay, so this is simply would be 20. Okay, question? Now the 2 by 2. N of A intersect B. Now the intersect one is going to be 100. A is divisibility by 2, and that would be divisibility by 3. It's going to be 2 times 3. Okay, 2 and 3. Now we simplify it. If you simplify it, that give you what? That give you 50 over 3. It's not divisible, so get the bracket. If you get a bracket, 50 divided by 3 would be 16 something, 16.6 or something. So we call it 60. Okay, any question? When you want to ignore the decimal, just use the bracket notation so we know what you did. Similarly, is going to be N of A intersect C. Going to be 100. A is divisibility by 2. C is divisibility by 5. That's nice. It's 100 over 10. You don't need any bracket, that give it 10 because it's divisible. Okay, then you want 1 B intersect C. B intersect C is going to be what? It's going to be 100. It's going to be divisibility of 3 and 5. So 3 times 5. Okay, 3 times 5, we can simplify it. Okay, simplify by 5, that gives us a 20. Okay, so that's going to be 23rd. 20 is not divisible by 3, so get the bracket. It's going to be 6 something, which is going to be 6. Okay, so that's a 2 by 2 one. So we have to go for the 3 by 3. So 3 by 3 would be A intersect B intersect C. Okay, so the total one is going to be 100. Divisibility by 2, divisibility by 3, and divisibility by 5. Okay, 2 times 5 would be 10. So you simplify it. So that gives a 10/3. Okay, that would be 10/3. So we have to use a bracket. It's going to be 3. So we have all the numbers that we want. Any question? So just use, these, make sure you use these integer parts, okay, to get this, okay. So now we are ready. Go back into the formula, substitute, and get the result right away. So the total number of integers less than 100 that are going to be divisible by 2, 3, or 5 is going to be, okay, the single one was 50, 33, and 20. minus 2 by 2 intersection 16, 10, 6, 16, 10, and 6 plus all intersection 3. If you put them together, the first one would be 103, 103, and this is going to be 32, 32, and plus 3. That would be 74. So there are 74 numbers less than 100 that are going to be divisible by 2, 3, or 5. So that gives you 74. Okay, so this problem can be, can be a little bit technical if you are going to be doing in number theory, because 2, 3, and 5 are prime numbers. Okay, sometimes you get 2, 4, 6, then you have to modify this type of information, but we don't do it. And basically, it's going to be just, they are going to be relatively prime, because we want to use that format that we have, nothing from arithmetic. They don't do it in this type of procedure over there, but it's a nice example because of you just design it. It's consistent with our formula, but just make sure that we explain it for us. And this result cannot be a decimal number because this is just a number of times in it. Okay, any question? So that's number 2 for the addition one. There is another one, very nice one. That would be a combination of letter of alphabets and some other related problems, but we have to wait. We need something else to be able to take care of that problem. So we come back to it. We come back to it, and we have 2 very interesting case for this. You know, the alphabets of English alphabets, A, B, C, D, etc. Those words are different combination of the letters. So sometimes you may be interested in some to exclude some combinations. Okay, you want to know how many times you can make letters of alphabet use so that you are not going to have combination like car, bench, etc. But that's interesting, another very interesting problem. But we have to wait because you need to do something else to be able to come back to it, okay, to get these numbers. Okay, any question? So that was our first rules, if you like, addition rules. And for the time being, so far, so good with these problems. We'll wait for the next one. Now, let's touch the other one too. We have time. This next one is quite interesting. Okay, again, for probability. You know that if you are in probability, you have to find the probability of A or B. Then we have something we call it probability of A and B. Okay, what is the chance of I get a raise in my salary and buying a new car? So that would be a combination of these, these 2 events are going to happen. Now, in order to get to those problems and the rest of the counting problem, anything else you want to know, you have to use the so-called multiplication rules. It's quite interesting. We already used the multiplication rules, but we didn't use it in this concept that I'm going to talk about it. Okay, so let's check this one. It's this is the big one, and we try to give you some examples so that you get the idea for future application. Okay, so it's a multiplication rule. So addition rule is done. So we go with the multiplication. We are probably in part of the section 9.2. It's very dense section. Try to get something out of it with the time that we have. Okay, what's multiplication rule? Remember the sets, we talk about it. If 2 sets are given, we can find what? The product of 2 tests. Remember Cartesian product? Cartesian product is just a collection of order pairs. And we talk about it if you have 2 sets, A cross B. The number of the elements in A cross B was the number of the elements in A times B. It's going to be called product rule, but in different format. Okay, let's remind you what we used to use. So this is what we know, and then we put it into the new format. We call that You see, if you give me two sets, if A and B are going to be what? Are given finite set. Finite sets means we end up somewhere. We're not going to go on forever. Okay, 1, 2, 3, 4, 5, it's finite. But for the counting numbers, 1, 2, 3, 4, dot, 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 no, it's not finite. So this argument can be used only for the finite set, okay, the terminated set. If A and B are given finite sets, you know that, then you see the number of the elements in A cross B, their product, order pairs, is the number of the element in A, okay, number of the element in A, times the number of the element in B. That's classic, okay? If the set's given to you, just use these type of ideas. And it can be extended. You see, this is A and the B, you can have A, B, C, D, etc. Now, how are we going to use it for this type of procedure that we're going to have now? You see, this simply will tell you that if you want to make an order pair, if you want to have an order pair, you need one member from A and one member from B. So how many members do you have in A, N of A? And how many members do you have in B? It's going to be N of B. So this means you pick one element in A and you pick all the one in the B. So the second one, all the one in B. So this means if you give me a procedure, you see the general case is going to be, you see, if you want to do something in general, if you want to do something, if you have case sets, if you like, case sets of these, okay? So in order to get the products, you are going to have, you have to go, the first action is going to be picking the members from the first set. So how many numbers can you pick the numbers from this first set? We're going to call it N1 for the first sets. Then you have the second sets. How many numbers or how many ways you can pick from the second set? It's going to be N2. You know, 2 times 3, 6, for example. But if you continue, if you have something called N3, then you can go on forever. You see, you can go on forever. You can go on forever. Or sometimes, you know, suppose you end up with, and we call it NK. So in order to do the job, okay, in order to do the job would have K steps. Step 1 picking the from the A, step 2 to 3. So in order to do the job, which contains K steps, so what we do is we are going to break it in different parts. Different part means the first step would need N1 ways, N2, N3, Nk. So the total job is going to be the product of all of them, N1, N2, N3 to the Nk. So if you want to use it in word form, it's the one if and operation. And most of the operation in everyday life is of these categories. So if an operation, I forgot about sets. If an operation consists of K steps. K steps, and each step, each those sets, each step can be done, okay, can be done or can be performed. Can be performed in Ni ways, or I equal to 1, 2, up to the K. Then the total job, then the entire job. The entire job, entire operation. entire operation can be done or can be performed. Performing what? In N1 times N2 times N3 up to the NK, okay, NK base. This is called product rule. You see, I start with it. This is just a set, really. So we just started with 2 sets previously, which is forming the order pair. If you go with the 3 sets, you are going to have the triples. But we bracket the actions that we're going to have. Action that we have, okay, then we put them together, all together, so that would be the total number of the ways that when this means this is just the total number of the ways that you can have, and we call it K tuples, if you like. Okay, those order pairs, triples, etc. Okay, so this is going to be called a product rule. Product rule, very popular, of course, used for probability. If you want to find the probability of A and B, would be probability of A times probability of B. But in probability, you have to put some condition on A and the B. Okay, many operations. Let's give you examples to see how we're going to do it for the product rules and their applications. It can go on forever. Everything else you want to do, this is the foundation, the multiplication rules. Okay, so classic one is just writing a set, finding the order page. That's classic. But the everyday life one, if you like, these are going to be the one that we're going to have. Okay, so you can't miss it, the product rule. And so give you some examples to get the idea of what's going on. I give you one on the test. Okay, something nice. So let's start with this one. We want to know how many, okay, how many strings, sequence, if you like, strings of 3. Okay, how many strings of 3 can be, I mean, of length 3, can be formed from a 26 symbol okay, symbol of alphabet, 26 symbol alphabet. This is going to be the one. Okay, you have these 26 letter of alphabets. So we want to put 3 of those together. Okay, 3 of those together, that give it a string. You know that we usually took the string of 0, 1, 0, 1, 0, 1. So in this case, this is going to be the letter of alphabets that are going to form. Okay, so the solution is going to be, see, let's see how we're going to make this. So this is going to be the job that we're going to be interested in. So what you are going to do is you are going to pick one letter here, 2, okay, and the 3. Okay, these are going to be the boxes, if you like. And you want to put these boxes together. So your source is 26 letter of alphabets. Okay, so if you want to fill up the first place, if you like, how many choices do you have? You have 26 letters. So you have 26 choices. So there are 26 ways that you are going to fill up the first part, first positions. And when we go to the second position, it's going to be the same thing. There is no exceptions, okay, no restriction, if you like. So you are going to have 26 choices for this one too. And for this one, again, 26 choices. Okay, so if you put them together, you know, you are going to do it in 3 formats. So by the multiplication rules, the answer would be 26 times 26 times 26, which is going to be 26 to the 3rd. And it's going to be 17,500 576 ways. So there are 17,576 ways that you can form these strings of, okay, of 3 letters of the alphabets. Any question? Now, the popular problem for these classic multiplication rules is the license plate. You know that each license plate in California, of course, you get what? You get 7 letters and number. So we usually have 6 letters, I think, and 1 number. In different states, it's going to be different. So how going to they make it? Okay, so how many can you make of those? So that's a very popular problem. They just change it a little bit, but you have a couple of them in your book. Let's write this one too, and then we continue next time to get the application of these. There's some applications, and then we put them together. We come back to the previous problem we start. Okay, any question? So let's get this license plate problem. Have one in your review, but you have to read it carefully because in different states it's different, and we may give you different restriction. So what's the license plate problem? In this license plate problem in your review, I think we talk about different types of cars. Okay, you have compact car, different engines, okay, different transmission. This is other similar problems. So let's do this one. Suppose a license plate for different states. A license plate contains, okay, contains 2 letters, 2 letters, followed by 4 digits. 4 digits. Okay, so 2 letters, 4 digits. That's going to be the one. So what's going to be the question? The question is, how many can we make? How many? Okay, how many different? How many different license plates can be printed? Can be printed by with this condition. I'm going to give you 2 restrictions. The first restriction is part A. If no letters or digits can be repeated, no letter okay, if no letter or digit can be repeated. This is one case. The other case is repetition alone. Okay, so the other case is going to be if repetitions of letters and digits are going to be allowed. So read it carefully, whatever it is on the assignment or just a preview one of the test. Similar things would be given to read it carefully. Okay, so again, this is the action that you divide it in different steps because you have to pick 2 letters and the 4 digits. So there are various possibility for this action. So we have to do it using we can use it using multiplication rules. Okay, are you ready? Solution. Okay, let's do the case 1. Case 1, no repetition is allowed. Okay, let's see how we're going to make a license plate. So if this is going to be the license plate, so your license plate needs some letters. Okay, some letters, you know, you have 2 letters, 1 and 2, and it follows by numbers. So 3 numbers, 4 numbers, yes, 1, 2, 3, 4. So this is going to be your license plate. Remember, no repetition is going to be allowed for the first one. So we go for the letters here. Okay, so for the letters, the possibility for the first one, you have 26 letters of alphabet. So the possibility is going to be 26 for the first one. For the second one, how many choices do you have for the second one?
25.
25, because the restriction is you cannot repeat the letter. So you already use 1 for this one. So it's going to be 25. Yes, very good. So that's going to be the one. Okay. Now we go for the numbers. Numbers that we can use is going to be 0 up to 9. Okay, 0 up to 9. So the first choice for the first one is going to be 10. Okay, that's going to be 10. Okay, the first choice. But you cannot repeat it, so the second one would be 9. The third one would be 8. And the last one would be 7. Okay, they use digits, not numbers. Okay, digits, so you can have 0 too. So by the multiplication rule, possible plates. So this is going to be possible plates. Plates can be made are going to be what? It's going to be 26 times 25. And this is going to be 10, 9, 8, and 7. Put them together, that will quite a lot. 3,276,000 plates for the first part by the multiplication rule. Any question? So just make sure that you don't miss those type of ideas that we have. Okay, question. But how about if you, okay, if the repetition is going to be allowed? So if the repetition is going to be allowed, this is going to be the license plate again. Okay, there's a plate. And this is going to be the number. Okay, for the letters this time, that's a letter, and these are going to be the numbers. 2, 3, and 4. Okay, the first choice over here is going to be 26. Since the repetition is allowed, you can use 26 again in here. Possibilities that you're going to have. And for the numbers, the same case. You can use the 0 from 0 digits to the 9. So it's going to be the 10, the 10, 10, and 10. So in this case, possible plates are going to be much more. So we have a 26 for the first place, a 26 for the second place, and then the 10s. Okay, that's going to be the one. It would be quite a lot, 6,760,000 license plates is possible to get these numbers down. Okay, any question? So that would be the first part of these type of ideas. We are going to continue on on Wednesday, but I need factorial notation, so I quickly remind you that one so that we are ready for it. We are going to talk about the permutations of the numbers. You have a set of the objects, then you would like to switch their order if you like. So the number of the time they're going to switch, or the number of the time that you can do this type of operation is going to be called a permutation. And that would be nice. We need it. Then when we are done with the permutation, that would be all we are going to do. But let me just quickly, I know that you know it, but just remind you that this is what we need as a remark, and we come back to it and we finish it on Wednesday. Okay, so what is this? You know that the product of and if an integer, let's write down, finish it. If n is going to be a non-negative, means it's positive or zero. Non-negative integer. Okay, non-negative integers, then n factorial. N factorial. N factorial is going to be denoted by, okay, this is it, n factorial. This is the way mathematician look at this one. And is defined by, the definition would be 0 factorial would be defined to be 1 for some reason. N factorial is the product of all the numbers up to the n. All the integers, of course. 1, 2, 3, n minus 1 times n. So that would be the definition of the n factorial that we're going to use for that second problem that I talk about it, even that hat problems, you need this one. So some, a small one, that small quantity that we use are going to be the 1 factorial is 1, 2 factorial, just 1 times 2, which is 2. Okay, and the 3 factorial is 1 times 2 times 3, which is 6. Okay, you know that 4 factorial 24, 5 factorial 120. But the observation that we need to remember is this one. Note that if you give me n factorial, I can shrink it when I write it down. It's a 1, 2, 3. Look at this one. Up to the n minus 1, then times it by n. You see this part over here, since this is up to the n minus 1, I can call it n minus 1 factorial. So n factorial is equal to the n minus 1 factorial times n. It would be very useful in simplification the problem. So we can stop anywhere we like. Okay, I stop at n minus 1, so the next number is going to be n. So 7 factorial is 6 factorial times 7, for example. This would be very useful to create a formula. Okay, that's it for today. We have one more thing to do, we get the permutations. Then we come back, we combine them with that problem of the addition method. We get a couple of nice more examples, but we need this one to go through it. Okay, that's it. Any question? So I post that practice quiz that we have, and the final review, you can start looking at those. We're slowly getting through the final because we don't have much to do really to get this. It depends, how far we can go. Sometimes we don't get time when we get to these, but sometimes we have more time. So it's not bad, but I'm not going to make it complicated for you. I'm not to talk about too much, but it's nice to get to the Wednesday. Then we can practice on Monday and give you the quiz on Wednesday, and we have time to go over the final review. Okay, have a good one, and see you on Wednesday. And there is going to be your last sets of assignments. I will post the numbers. Then you bring to get your last 10 points on the assignments too. Okay, have a good one. See you on Wednesday. Bye-bye.
Thank you. See you Wednesday.
Thanks, Professor.
Thank you. Bye-bye.